Okay. Good. Okay. So, okay. Hi, everybody. Thank you for coming. So I'm going to be talking about this tool, the planetary spectrum generator, and how it functions, what can be done, what can it do, and what it cannot do. So the tool is an online tool. So you can go to the web and run things on the web, but you can also download the software and install it in your machine. So what is this tool? This is it's effectively a radiative transfer tool. So what it does, it follows the photons as you go through an atmosphere, through a planet, and then you can also synthesize what happens to those photons when it reach an instrument and what the noise performance is. So because it's actually done to be very realistic, one of the things that I have encountered when talking to people when they use it, that there are a lot of options. I mean, there are a lot of entry elements on the on the website. Then it can be, if you don't know about it, it can be a little bit overwhelming. So the idea of this is to go through them and to see what it means, what it don't mean. The moral of the story is that if you don't know what a number does, the defaults tend to be right. So normally has been a lot of effort that I spend trying to work with the defaults, so the defaults will give you something meaningful. And I think that's what I think one of the big assets of the tool is to make sure that if you don't know anything about specific details, you can run a calculation and get reasonable results out of it. So the code can synthesize planets and exospheres. And exospheres are cometary exospheres, which are mainly in non-equilibrium, what we call fluorescence. It can also do plumes. And then I will talk, I mean, you will see how you can actually do Enceladus within Enceladus or Europa. So the thing about the thing about the tool is I want to explain you the blocks that go into how we follow the photons, and then how the photons are being affected by the different components. So, and also I want to show you the interface, so then you can go back and see, So first of all, this is the website. Normally you see these sliding things.
What's the link?
The link is psg.gsfc.nasa.gov. psg.gsfc.nasa.gov. So the thing is this: every time you run something, and I always say, when you are, your simulations are not working or whatever, something happened, if you get frustrated, just come and press reset here. It will bring it back to basic state, and you're from scratch on beginning. So that, I think, is one of my favorite buttons. I press reset, and I'm back to square zero there.
What's your favorite?
The reset one.
Oh yeah, okay.
You click that one, you're back to, okay. So how this works? So if you go in the upper bar here, this is where the help is. All the help documentation is in the upper bar here. So if you go to the about the tool, so this is what the tool is all about. So the tool is, what it combines is, if you have done modeling of atmospheres before, the biggest problem is that there are humongous amount of reservoirs of spectroscopy and a humongous amount of modeling capabilities, and each of them functions in a different way. You have to become a computer scientist expert to run them in most cases. So the main thing I did is, first of all, I collected all the molecular analyses, the most important ones, into a standardized format, and those are all that ones there, and I always keep adding. So the core of the functionality is to keep those updated as much as possible, and every day we work on trying to make those up to date. The other thing is, what is optical constants? If when you reach the surface of a planet, or you're looking at a planet that has no atmosphere, you're looking at the surface components. And this is, you need to know the reflectance of the planet, or the comet, or the asteroid, or the optical constant if there are ices and stuff. So those also another big collection of databases have been homogenized for PSG. I think that the biggest element here is the atmospheric models. Those are the main things. So this is they do is, these are general circulation models, ephemeris models, calculators, and all those things, which are very nice, because if you don't know anything about the planet, you go there and it will give you some sort of state of the atmosphere, which works in most cases. Then, of course, if you're an expert and you have your own general circulation model, you have your own atmospheric model, you can actually update, of course, and do your own atmosphere. But for the people who don't have these things, you can actually use some of the things already integrated in PSG. And then once the photons go through the atmosphere, do all that, then you have to see what the instruments are doing with those photons. So what we did, we integrated different instrument models, which are known facilities that we have, orbiters and telescopes and stuff. but you can also create your own telescope, and you will see it's not very complicated to define your performance parameters. It's very basic, but it does a very good way in calculus noise. You will see how the elements of calculus noise.
Is this one of the links?
Yeah.
Just the home?
Yeah.
Oh, okay. Yes.
And then what it all is ingested into these radiative transfer codes there, and then they have PUMAS is a component of the code, and I will talking about that one. So PUMAS is our planetary radiative transfer code, which is the core of almost every calculation. The one is that I ingest all these numbers and create fluxes. Then the non-LT codes, those are the ones we use for exospheres, and we have a surface, the GCM code, and we have a scattering code and other codes. All of them are ingested. So what you do is you follow the photons, and I will explain you a little bit how this works. So first, let's go to the website. There are 3 elements of a simulation. The first one is the target and geometry. So it says what are you trying to look and how you're looking at that object. Then the atmosphere on the surface. What is the atmosphere made of? The surface component. You can also do retrievals, and I will show you a retrieval for that. And then what instrument you're using to make those measurements. Those are the 3 blocks here. All of that is encapsulated in a configuration file. So normally what it is a text file that has all these parameters listed. Only one file, I call it one file that run the whole thing, but it's one single text file that runs all the codes. So what I call it, the web interface, I call it, it's a fancy text editor. At the end of the day, you're always modifying a big file that has all these numbers. So the key thing for you is learn the interface, but also learn that config file that I will show you a little bit about it. So that config file is the driving force around it. So once you understand how that works, then everything becomes much more understandable.
What is it called?
Config file, and I will show it here. So if you go next to my favorite button, yeah.
Oh, config.
So next to the reset thing, you have this thing here that says download. So this is where it shows the status, the current configuration file. And it looks like this. So what is this file? So the file is a text file. It's in an XML format type of, and you see it has this has a name of a parameter, and then it has the parameter value there. And then you have the object, you have the geometry, you have the atmosphere, you have the surface, and you have the generator, which is the instrument components. So the main thing is that your web interface is actually editing this. Every time you click something, you're actually modifying this text file. So once you see this is kind of cryptic for you, you say, well, what are these numbers here? So the main thing, every time you run something, check this config file, what is it doing? And so then how to know what those numbers are? You go to where it says remote operation here. It says parameter lists, and it tells you the parameter and what the values are, the ranges of the numbers, and all the stuff about those numbers. And I will explain now how these numbers are done, but this is just to tell you how this works. So remember, what you're doing with the web interface is editing that file in some way, and then run a simulation for it. So let's do one quick simulation. Let's do reset, as I say, my favorite button. We go back to the basics. What is it doing is actually deleting all the stuff you have, and it is replacing your configuration file with a default one, which is this one is a transit for a exoplanet as done with James Webb. So in this case, you see this is an exoplanet called GJ1214b. We are at 12.95 parsecs from this object. We have some basic chemistry for this body, and then we're trying to get something from 0.4 to 20 microns, and we want to see what comes out of that. So what you do is you click here, it says generate spectra, and this thing will use that configuration file, and it will run a spectra that looks like this. So this is what you would expect to see with James Webb. So the traces are pretty, you can see this is wavelength, here's a transit, and this is in a particular unit called contrast, which is for transits. And it also simulates the error bars, and that what will be the transit looking like. This is the graphical way. You can do zooms and stuff like that to see how the features look like. And then if you want to download this file and you do your own graphics for this, you click where it says radians here, and it looks like this. it tells you what it did, all the parameters, and then it gives you the wavelength here, and then the labels are listed here. Let me show you. So these are the labels, and it gives you the same numbers, but in a text format. Yes.
One question is the input file from the parent star. So do you need to have the?
Yeah, I will explain all that.
File.
So I just wanted to show you how the numbers are coming out. So the main thing for you is that, you know, again, reset. You click one of these templates. Let's click on the exoplanet one, and it will give you the transit spectra. It gives you how every subcomponent of the atmosphere absorbs the molecules, and also tell you what the noise come from, which is very nice. If you want to know who's killing your detection, you can see, for example, in this case here, you can see that you're getting a lot of noise by the telescope is warm enough to kill your signal, or what is killing your sensitivity. So then you can investigate how to improve the sensitivity, or what is the limiting factor for your retrieval, for your measurement. Okay, so as you see, these are the free blocks. So let's go each of them, and then we're going to do different ones, but this is where we go into the details. So typically, again, we do reset, and we go to this one, the target and geometry. So what you put here is information. You see there are a lot of fields here, and you're like, oh my God, what are all these numbers here? So the main thing is, if you don't know what they are, just leave them. The defaults tend to be okay, but I will explain you what the numbers are. So there are two boxes here, two areas. So the upper one tells you the relationship of the planet and the host star. So if it's an exoplanet around a host star, you know, you tell information about the host star and the planet. If you are looking at something on Mars, for example, well, it's going to be Mars, and the host star is going to be obviously our sun. So the numbers here you can see is the diameter of the object in kilometers, the density in, you can put mass, gravity, or density, and this is the gravity and the mass of the object. How far this object is from the star, the velocity between the object and the star. This is, if you do radial velocity studies, you need to have this number. These numbers are very cryptic, and this is tells you about an exoplanet. They tell you how is the orbit of the exoplanet. If you don't know them, leave them like this. They are being populated by itself from a database. Then the type of star. This is a GJ1240b. It's around a M-type star. You can change different types here. The temperature of the star and the size of the star. So for example, if I click here, Mars, for example, it shows me the numbers for Mars. If you click Earth, it shows the number for Earth. So you see exoplanets or anything, it has its own set of properties here. So again, this up here is just between the star and the planet. You didn't tell anything about you yet. So this is where it gets interesting. This is where you say, okay, how you are looking at that planet on the star. So here you define how you are going to be looking at the object. If you have an observatory like James Webb or JWST, you have to pick the observatory mode here. Typically, that's what you do when you're observing something from a telescope. But for example, if you are orbiting the planet or the body, you will put nadir, or you will put things like LEAM. All this stuff is you are already above the planet going around. So this is not relevant for exoplanets, for orbiters. And if you're sitting on the surface of the planet, you're going to put something like this. You're looking up. So you are on the surface of the planet, you're going to looking up, and you want to see how the flux looked from the surface of the planet. So I'm going to go back to the template here. Yeah, this one. I'm going to load it again. And if you simulate, this is how the exoplanet looks like. So you see you have the host star. This is the orbit. And it tells you that the whole planetary system is very, very small, 0.0021 arcseconds. It means that the whole thing is super microscopic for the field of view. And this is how the planet looks like if you are sitting on the star, and this is how you see it from afar. You see that the planet is dark. You're looking at the night side of the planet because it's in front of the star. So because this thing has a 3D calculator of the exoplanet, if you say now, so what it's doing now is that for this planet GJ1214b, it tells me that the exoplanet right now is over there. So it's not in transit right now. And you can ask the machine, this is because we put right now, this is the time right now. If you say, tell me when is going to be the next time the object transits the star, you click on T. And it gives you here in UT time when it's going to transit. And it shows you now it's going to be in front of it. And it tells you all the parameters about that transit, how long it takes, You know, it takes, it's an orbit of 1.5 days. The transit time, the duration is going to be 3,000 seconds. So you know everything about the particular transit. Imagine that you want to do TRAPPIST. TRAPPIST 1E. You do now, and this is how TRAPPIST looks like. Because has a low, you know, you can actually put any exoplanet, has 4,000 exoplanets are here, and you know exactly what it is. If you put T, it will put the object into transit over there. So it does it, you know, it's pretty graphical. Again, it tells you the distances and stuff like that. Let me go back to, let's go to 1214B. Okay, they're gonna put it in transit. So, and you can see here, I'm gonna go off them from other cases, but I just want to focus on this. So remember, the upper part is the star and the planet, and then the lower part is your geometry related to that. Okay, so once you define that, you have the geometry. Now we need to tell properties about the planet. And this is what I say, it gets, people, I think when I'm talking to people, this is what it gets complicated for people. And I want to spend a little bit of time about this. So this is what you explain what the atmosphere is made of, what databases are you going to be using for modeling the atmosphere, the structure of the atmosphere, the surface, you put everything, you tell everything about the planet itself or the object that you're trying to investigate. So this is the core of the thing. Again, PSG will look at templates and things that are accommodating for the object. If you're looking for a comet, it will give you some accommodating thing for a comet, and it will do a lot of assumptions. But if you want to play with this, you need to understand how this works. This is the core of the tool, if you ask me. So in this particular planet, this is how, I'm going to show, I want to focus on this first. So this is how the, yeah, sure. You come here, you click in where it says atmosphere and surface change. And if you go scroll down, you see these things here. So,
and then how you get this particular profile?
Well, this is for a JWST, this particular exoplanet. And I will show, we can do other ones, and I will show you how to get different ones. So what this is showing you is the temperature across pressures for that exoplanet. So if you are in that planet and you want to look, you know, it will tell you the temperature pressure profile, which is critical for doing any calculation. And this thing here is the abundance ratios. And those are, you say, how you got those numbers there? Well, and I will explain you how I got those numbers there. But it means that there are all these species, and I have a lot of abundance ratios and stuff. You're thinking you did some voodoo magic there. And I will explain you how that voodoo magic works for the exoplanet. So you see, you have all these species with very precise numbers there. They all came from a model, which actually, if you don't know anything about an exoplanet, this model works pretty nice. And it's actually a combination of two models, and I will tell you what they are. One is called the Parmentier model, which is listed here, and the Kempton model. So again, this is what the code is telling you about the atmosphere and what it's made of. It doesn't tell you anything how you're going to run the simulation. It just tells you how the structure of the planet is. And this is what I want to say. This is just telling you about the structure of the planet here. Then here, up here, in this block here, is you say, okay, I want to make a, let's imagine that I want to make a simulation with oxygen on it. So in this case, you say, I want to take that profile and I'm going to use only oxygen. I want to see how the oxygen signature looks in this exoplanet. So you put here oxygen, and then you say, great, there are 1,000 species. You can pick any species here. We can oxygen, or we can do methane or something like that. And then here you say which database you're going to be using. If you don't know about it, pick Hydron, which is the most accurate or more reliable. And I have a lot of information about this, which is heat number here. And then you say the abundance of this molecule. This is what you say how abundant this molecule is. If you put one scalar, what it does, it takes the profile, which is here, and scale it by 1. If you put 10, it will scale the profile by 10. So this is the way you scale profile. If you say, no, forget about it, I want to have a constant mixing ratio of that molecule across the profile, you come here and you put 1 ppm. So now it will have methane, 1 ppm profile across the whole planet. Yeah.
So if you add something to the vertical profile section,
yes.
not already there.
Yes.
If methane wasn't in that section,
yes.
and you added methane, you would have just like you would just have like a straight.
Yeah, so you can, for example, if you want to have a profile for a very peculiar profile. Imagine that you have your molecule. We're going to call it John, whatever, or whatever. We will make it something real. We can have MG, whatever. So we make an abundance of 1 parts per million, okay? And we want to make a profile that is a layer of that molecule between 1 bar and 0.1 bar, 0.1 bar. So you are creating a layer of that molecule at that particular layer, and you say add profile. So now you see that thing appear there. That is your new molecule, MGH there. Once you have it there, you just created a profile for that particular molecule. You just created your own profile there. And then you come here and you say MGH, and then you use that one, you say 1 scalar. So now what it's gonna do is gonna run a simulation with MGH using that profile. So that's the way you connected the profiles and the thing together. We can go more in detail, but this is more the basic idea of this. You see, this is the core thing. Again, if you get a little bit lost, you see these color things appear, pop up next to it. Just click on this. Every time click on the I number thing if you get lost. If you click on this thing here, it tells you, it gives you a help. It tells you, you know, what the numbers are, how to modify the numbers. It tells you about the databases, where they come from, and all the stuff. You can read all this. It's been very explanatory. And again, if you don't know, leave it as it is. The defaults seem to be okay. But just read, this is what the core of the thing is all about. Yes?
Basically, all the neutral species, right?
These are neutral species. There are no ions. No ions yet. That's a good point. So going back to say, okay, let's imagine that you say, you know, I don't know anything about this exoplanet. I just want to use defaults. Don't complicate my life. So, okay, let's go back to life. Let's do reset. And we go back to this exoplanet here, and we have this default. So now if you want to have you can pick templates. You can add your own profile. If you put up a free file template, you can provide your own profile. But if you want to use some of the models PSG has, you can click here. It says I'm a fair template, sorry. And this is where the different modules come up. So this one is, I was telling you, is the Parmentier-Kempton model. So what it does, it based on the distance, it's explained there, based on the distance of the star and the size of the star, the planet, sorry, and all that stuff, it computes the vertical profile of the planet, and also tells you, it uses some equilibrium state equations from Kempton, and then use that to produce the chemistry of the planet. And then you can, you know, this is based for a particular type of metallicity. You can change the metallicity of the planet. You can change the CO ratio. You can play with those things. Imagine that you say, I want to do a condensate with a massive amount of metallicity, and it will produce a very heavy atmosphere in some way. So in some way, you can see it synthesizes for you a profile based on different conditions. You can play with that. This is for a giant. If you want to use, you know, I want to use Earth database. It's called MERA. This will use servers from Goddard, and we'll get the atmosphere of the planet. I will show you later for our planet. You can use the Mars climate database, and it will tell you the profile from Mars right now. So if you do like this, this is how the profile of Mars will look like. So you can choose different GCM cores to give different things for you, and it will give you all the abundances and all the stuff for a particular planet. So this is where you put templates. You can also say, you know what, I'm gonna use a Titan basic one. Just do load, and it will give you this is how Titan looks like. So you can pick very different templates and do things like that. This is about the atmosphere. Below here is about the surface. Okay? This is once the radiation reaches the bottom of the planet, it hits the surface, okay? And then radiation comes out. So here is the temperature of the surface, the albedo, the emissivity, and this number here, which is magic, is the Healy-Greenstein phase function. If you don't know about it, leave it in zero. It's the default, and you can play with, depending on the angle that you look at the surface, it will change the phase function. So this is called a Healy-Greenstein phase function factor. It's mainly useful for small bodies. So inside the code, if you go back to modeling here, sorry. Come on, disappear. Oh, sorry. Sorry, guys. Sorry. Okay. So if you come here, this is what the simulation is all about. So it's following the photons as they go through the atmosphere. It will include scattering, going through clouds, and it will also touch the surface, and it will compute the radiation coming out. Okay, so you're following how the radiation goes, and it's all about, we went for the radiation came from the star, hit the planet, the radiation of the planet is being emitted, then it goes through the atmosphere, and then what happened with the photons, how you define your telescope or your instrument, how you look at that. So then you come to the instrument section, which it looks like this. So again, there are a lot of numbers. If you don't know, you can use defaults. I will show you what the numbers are. These are the key numbers are. First of all, you define the wavelength range, the resolution, and then that's three things here. These are pretty obvious. Most everybody knows what those numbers are. This is the range, this is the synthesis range. And then you have this free thing here called what are these things are? When you look at on a planet, sometimes you don't want to look at the continuum emissions, like the surface. You want to say, I don't want to look at the surface. I want to look at the atmosphere on. So you can disable the continuum fluxes. You can also disable the atmosphere. You can do that with that one. Or you can also disable stellar templates. When you say that the star is an M-type star, it will use an M-type star stellar template. So if you don't want to use that information, you can avoid it. So it's a way to play with the numbers. It's give you more flexibility. No worries. Yes.
You said the M-type star. So can you discriminate between the M1.5 and M2?
No, I'm using M-type star.
Or just M?
Yes, I'm using
So
M-type.
what do you use for M as a default?
I'm using
M5 or M0?
I'm using the Kurutz model for M-type star. I think I don't remember what number it was.
What do you think?
Yeah, I can look it up.
Okay. And for G the same?
Yes,
So
and
you
for
use
G, I'm
one
using.
G, one M, okay.
I think it had a temperature. So.
You can change the temperature, but it will not modify the thermospheric abundance of the star. Remember, the star normally produces features in the spectrum, and normally when you look at typically relative measurements of the fluxes, you will see that the star spectrum goes away. So typically the spectrum is relevant, but it's not a big component of the calculation. You will see how it percolates here. So this thing here says terrestrial transmittance is, what is it? If you are looking if you're using your telescope is located on a ground-based telescope, you have to enable this, and I will show you later for a simulation. So if you're looking from a ground base, you enable that. If you're looking from space, you disable that. This is what I think is the main thing about the tool, which I like a lot. You have a humongous amount of radiation units because the code preserves photons as they fly from everywhere. It keeps track, and you can compute fluxes in almost any unit you want. And most of those fluxes are absolute, and some of them are relative, like these things here. So you divide the flux of the planet by the star, for example. That's called I/F or contrast. Those are relative numbers. Something relative to another flux. And then comes to this. This is what I want to spend more time because it's a key component. So this is what you define. How is your instrument looking like? If you have a single dish, what is a single dish? It's a single small dish or a humongous 15-meter dish, something that only has one aperture, and the photons come from that aperture. You're trying to tell how big that aperture is. So in this case, it's a 6.5-meter dish, which is a James Webb type. It's a big dish. But if you have a small microscopic instrument, you can say 0.1, and it will be a 10-centimeter little mirror collecting your photons. This tells you how big your mirror is. Then you can choose different things, and you can have an ALMA array, you can have a coronagraph, you can have some funky stuff like we have an ExoMars, or you can have a LiDAR system too. And I don't want to go into the specifics. We're going to concentrate on a single dish because I think the 99% of the cases are based on that one. This is another number which I think is the most confusing for a lot of people, and I want to spend some time explaining this. So what is this, the beam? The beam is this. So as every time you measure an object, how big your resolution of a beam or your aperture will define how big your resolution is. So for example, if you look at an exoplanet, you have the object and the star in a single aperture. The object is so small that you tend to have all the flux will be diluted. It will be a point source with everything diluted around. Okay, but imagine, let's go back to this case with we are here. So we simulated here. You see the object here is a 0.002 arcseconds. This is microscopic thing. And then this is because, and then I can put different size for my beam. If I put 1 arcsecond, if it means that my beam is 1 arcsecond, it means that this thing will be only in the center, a small little thing surrounded by a lot of space around it. Okay, now imagine that I go to Mars, for example. I'm gonna go to Mars and I'm gonna say right now. You see now my beam here, my 1 arc-second beam is, because Mars is around 6 arc-seconds, I don't know how big is it right now, that will be our beam, okay? It shows the code will only get flux from that little area. It will not get flux from anywhere around that thing. So you see Mars is 4.8 arc-seconds here. If you do 0.1, now your beam is gonna be very small. Now we're in the polar area and you can see we have a very, very narrow, very small beam there. So the key thing about this is that the beam defines how big you are looking at the object. If you have normally for exoplanets, your beam always encompasses the whole thing. What is the number given? How do you know that number? Well, that number is normally given by the people who build a telescope. They will tell you, oh, my resolution is 1 arc-second or whatever. If you don't know about it, typically almost every telescope out there is diffraction limited. It means it will have a beam which is going to be very small and it's going to be defined by the size of the mirror. So if you put here diffraction, it will make 6.5 meters, and at that wavelength, the beam is 0.4 arc-seconds. So it will do it for you. We'll do the calculation for you. How big the beam is relative to the wavelength and to the size of the beam. Okay, so beam is very important. If you don't know, use diffraction. Diffraction is the standard, and I would say the most typical one for most of the cases. And then come here about the instrument. And these numbers are very difficult to explain if you are not a person who develops instruments, because they tell you there are information about the detector, information about the temperature of the detector. There are things that typically you don't know, and it's difficult to find them out. I would just gloss over them so you know more or less, but PSG has a lot of templates, and those numbers are already pre-populated for you. But the main thing is that, first of all, you define how big is the exposure you're taking. In this case, we do 0.2 seconds for an exposure. Then you say how many exposures you're doing. In this case, I'm doing 4,000 exposures of 0.2 seconds. And then I have, this is the number of pixels that I'm integrating to make that. So you're thinking that you're in the detector mode, you're adding those 8 pixels and you adding all amount of time. These numbers tells you about the detector properties. These are what people gets very opaque from most of the people. This is electrons. Every time you read an electron, every time you read the array, it will produce this amount of electrons of read noise. And then these things. These are very critical numbers. The manufacturer will give you those, difficult to find. These 3 numbers are interesting though. And I think these are numbers that you should always, when you do something, take a look at them. These 3 numbers make more sense. So what are these 3 numbers? The first number tells you the throughput of the photons. So if a photon reaches the mirror, how many of those photons you're going to be able to actually count, okay? So 1 is a perfect instrument. All the photons arriving to the instrument will go and be measured by you. Impossible. Normally never get that. If you have a very simple instrument with not a lot of reflecting surfaces, 0.5, 0.4.
So that's basically the end to end.
That's the end efficiency of it. Yeah. That's the end to end. And that's number. I will show you how those numbers are. You see that number, in this case, 0.2. Typically, the number is a typical number. Depends on the grading system. Some instruments have very pure numbers, 0.1. This other number is the emissivity of the optics. Imagine you have an optical system that is radiating, typically you do them very beautiful. They are perfectly reflective things. They don't emit anything. They are beautiful things. But occasionally they also emit light, flux, and that will produce noise. So here you tell how much of the flux of the optical system will be radiated. If you put 0, it's a perfect instrument. It doesn't radiate anything, which never happens. But if you put a number there, 0.1 is a typical number for most facilities, and I've been using that almost across everywhere because it's a typical way that typically, if you have a lot of reflecting surfaces, they will radiate 10% of the radiation that they can actually radiate. At least in your field of view. And then the last number is the most important one. It's the temperature of the optical system, the bench. So for example, if you have a 50 Kelvin optical system, and then 10% of that flux radiates, that adds to noise. So that's why people trying to keep the instruments cool or everything cool to minimize that. So people play with those numbers.
Is that centigrade?
These are Kelvin. That's right. These are Kelvin.
Okay. These are all Kelvin.
Yeah. So I will show you here, for example, and then this is for a CCD. You can have a NETDF, which is another type of detector.
Can you show me the template for the receiver?
Yes. You put here the receiver temperature. This is explained in the, if you click here, it tells you what the numbers are and how you put them back. And so you see every detector type has a different explanation. So typically what you do is you pick one of these already pre-computed ones. You say, I want to do James Webb with the prism and NIRSPEC. Do load template, and I give you all the numbers for that particular configuration. So you don't have to know those numbers. It give you all the numbers that I collected from the literature for that particular configuration. If you are, I don't know, you want to do ALMA, yeah, if you do ALMA band 4 load, and you see it's an interferometer array, there are 54 antennas of 12 meter. You define all the parameters of the optic of the.
What's G again?
G, that's the polarization.
Polarization.
Yeah, it's a number. 0 means no polarization, discrimination. 1 is with polarization. If it's dual polarized or not.
Okay, so whether we have
Yeah, you feed the light into it.
so we have polarized to be what? That
Yes.
is polarized.
Yes. Okay. So you see, you can play with the numbers. The key thing about this is you can modify the numbers. Again, if you don't know about it, go to the templates. I have spent substantial amount of time trying to make this right. So if you don't know anything about it, just leave this name below here. But you may say, you can play with the range, but these numbers gonna be probably okay. Yeah.
For the time signature, is it figuring that out based on whatever planet or whatever you're looking at, or do you have to figure that out?
You have to figure that out.
Okay.
So imagine that I give you an example. So let's reset here. And so we are in this GJ1214b, okay? So when you do a transit, typically, here it will tell you how long a transit takes, 3,000 seconds. So then I just put it there. You can choose anything. If you want to do one transit, you would put 3,245 seconds. That would be one transit, okay? So that's the duration of one transit. The problem, if you put that humongous amount of duration for an exposure, you will saturate the detector always. So imagine that I put that. Imagine if I put 3 to 48 and put one exposure, okay? So I'm just gonna do one transit and I'm gonna keep the exposure taking like crazy there. So the code has a very simple calculation, but it tells you that they give you a warning that you are saturating or oversaturating the detector. So 2 millielectrons per pixel were detected. There were 4.8 photons, which is a humongous amount of number. You should reduce your exposure to at least 0.3 seconds not to saturate your detector. They give you an idea. You should know better, but at least they give you an idea. So normally when you come back and say, okay, I screw up, that my exposure was too long, you put 0.3, and then you say 10,000 exposures. So now you do the same, and it give you a similar noise, but now it's doing it correctly. It's not saturating the detector. By putting the right numbers, the relevance about that is that the noise performance here, those numbers here coming out right. So if you look, this is very important. If you try to understand what is killing your sensitivity, you have all those numbers there. In this case, source means there's photons coming from the source itself. You're looking at a planet with a bright source, so all the photons from the star are the ones killing your sensitivity, which is a good side. You always want to be in that side. The source is limiting your sensitivity. If you start seeing things like the telescope is hitting you, okay, look for a color telescope. If you're gonna get a color telescope, it's gonna be that way. Huh? The detector is very important. If you see that the detector is defining your sensitivity, well, that's kind of a problem. But you need to find out what limiting factor is defining your sensitivity. Okay, so we talk about the exoplanet mode. I'm gonna go a little bit about the other ones. So let's go to, I'm gonna pick an orbiter. This is Mars, but it's applicable to any other orbiter, also for Earth wings. So we pick this template here, and we're gonna go for this thing here. So you have the same thing. This is Mars. These are conditions of Mars right now. But here you can see I define the geometry, and I say it's gonna be a solar occultation, and I say which spacecraft is doing that. And the machine has ephemeris for all the spacecraft around Mars. So it knows whatever each of them are, and it will calculate all the angles for you. So in this case, it's showing you that for this occultation, we are here in blue, and we are looking at the tangential point for the sun in that condition. So it's a very peculiar orbiter mode. Again, you can put, so in this case, the machine did a calculation for me. So if you come here and say, I don't know, May 2017, give me the ephemeris. The spacecraft was still in a funky mode. You see, it was not reaching the orbiter mode in the thing. So it was still error braking. So it shows that there was not a good, you can see the orbit is all over the place. But then if you come to 2018, last year, it shows you that the orbit, the spacecraft already reached the convergence. So it's now in the right place. And you can do calculations like this very, very easily in some way. So this is for example, if you pick, if you say, you know, I'm on Mars, I'm on Earth, and you do right now. So what it's doing right now is, it knows I didn't say where I was. I should have told it. Okay. So now it's doing, what it's doing, MERA is the repository of climatology for our planet. And I will show a little bit more about that. Imagine that you say, I'm looking at our own planet. I am looking up from the surface of our planet, and I am in Maryland. And actually, you can say I'm looking up to the sun. So you can, that's actually nice. You can say you're looking up to the sun, and you say, ephemeris, now. So now what it will do is, okay, there it is. So you can see we are here, it's daytime. It says that the sun is at 43 degrees from us. It went to the climatology database from the NASA servers here, and it got the structure of the atmosphere above us. But it obviously doesn't know it right now. So if you come here, this is how the profile looks like for our planet. But it didn't do it for right now because it doesn't know it now yet. It takes 2 months to collect the data on the spacecraft. So it's based on last year. Always when it doesn't have data for the future or the present, it always goes back 1 year. But it has a very small latency of only 2 months. So if you go back 2 months, it will actually give you the.
Yeah, so if it's more than 2 months ago, like December.
It's fine, yeah. It will actually pick it. So yeah. So yeah. So we'll give an example. We're gonna, for example, we can come here and we pick. Let's see. We're gonna January 4. Mary's. Let's see if it gets the right one. So the good thing about this thing, it gets you the full geometry, but also gets the climatology from this MERA database, which is pretty nice.
Yeah. How do you have drivers for the moon, for example?
Yes.
Geometry for the moon?
Okay, so well, you can see now it did it for the right time. So it got. This is how the atmosphere looked at the time. We've been testing it for Mauna Kea, and it works beautiful. So it's actually it's very, very nice. Okay, so what about the moon? The moon is here. So you can be in orbit around the moon, but I don't have any orbit. You can add. You can say. Oh, you want to look at from the surface? Yeah. You say looking up to the sun from the moon. Yeah, you can do that.
Yes.
And
you can put the latitude.
Yeah, you can put the latitude. Yeah, and they put here, I don't know, somewhere on the moon. Yeah, you say you're there, and then it tells you the angle, so you can actually simulate the condition. So you can do almost any object.
And then I can put in my exosphere.
You can, and then okay. So let's do that. Let's do that case. So here you define the geometry.
You know we have an instrument.
I know, that's why. Then in this case, we put that there's no atmosphere on the moon because the moon is not to have an atmosphere. But if you want to add an atmosphere, you can add an atmosphere here. You can say how many molecules are coming out the surface and stuff like that. You can do it that way. So this is the way it's done. Going back to I'm going to go back to the Martian one. The Martian one, which I think is relevant, is applicable for beyond any other object because there are a couple of things which are relevant for any planet that has a lot of scattering. So what happens here? In this case, I put only CO2, and I'm using the GCM CO2 abundance profile. And I have these two aerosols thing. So aerosols are very peculiar. They do a lot of crazy stuff into the atmosphere. They will extinguish the light, and they will also scatter the light. Treating that properly is a very complicated one. If you have an orbiter around Mars or Earth, treating that is a full body of research. And I'm going to tell you a bit about how we do it here. So in this case, we have this, you put here the two aerosols. You tell, you can choose different types of dust particles or dust models. They say dust, and we're using this one here. We say the size of the particles, one micron size. And this shows you how the profile of the aerosol looks like. And then up here, you see these magic numbers, Nmax, Lmax, and phase. So what are these numbers? And I will touch at the bottom. You can go into the search what these numbers mean. So the phase angle is the angle between the sun and you, okay, and the surface. So it's the angle between the three things. It's the phase angle. 0 degrees means that the sun is behind you and you're looking like this. You're looking at that thing. And then if you are looking at it's 180 if you are on the other side. So it's an angle between the sun, the surface, and you. That's the phase angle. It's very important for scattering. And then they come these two numbers, Nmax and Lmax. What are those numbers? So if you know a little bit about scattering, what it does is scattering is the light. The light normally shines through the particle, and then it gets scattered somewhere around. Somewhere it will go away. So you need to keep track of those photons as they fly away. So since the scatter could go down or it could go to the side, you have two dimensions components. Okay. So normally that what we call, every time the particle hits the thing, we call that the phase function. Okay. How many terms you describe? We have something we use Legendre polynomials, so they have the phase function. The more accurate you can define very sharp features in your phase function. Sometimes particles have very sharp signatures. In this direction, it will fly with maximum intensity, the photons, and some other ones it will absorb all of them. So all that thing is being described with this thing called Nmax. It describes how many Legendre polynomials you want to use. I know it's complicated. Sorry, the Lmax is the number. It's complicated. You can go in the help to learn more about it. If you click in the eye, it will explain more about it. So this is a little bit explained around here. And what is Nmax? Nmax tells you that how many angles you're going to keep tracking of the photons. If you put 0, you just want to look how the photons fly to you. If you put 2, it will look to you, and then also photons going back in the other way, to you and that way. If you put 4, it will look to the sides. So what it does, it keeps track of every photon as it shines everywhere, and then it comes back to you. So it has it more complicated. Because it does all this computation, it's very expensive, but it's very accurate. So normally, if you want to do a scattering calculation, you need big numbers for Nmax and Lmax. Your calculations go to the square of Nmax. So if your calculation takes 1 second, if you put Nmax 10, it will take 100 seconds, roughly. And in Lmax is a linear relationship. So normally the code, if you run it right now, let's do an Nadir calculation for example. So yeah, let's do this guy. So if you do this calculation, you see the code is complaining that you don't have enough scattering components. It's telling you that you should have more. The machine is telling you for this particular dust particle, because it knows the properties of it, it tells you that you should have at least Nmax equal 5 and Nmax 20 to capture some of that structure. So if you don't know about it, PC will complain and let you know. Typically, if you don't see any complaints, you're probably fine, don't worry about it. But it's always remember that those things are very critical when you do scattering calculations. Okay, let's go back to another case, and for people who do comets. So comets are peculiar. Comets are peculiar because all the things I've been telling you is about radiation coming from an atmosphere which is layered and it follows a very classical aerostatic equilibrium case. Comets are an exosphere. The molecules are flying out of the nucleus, okay? So in this case, this is comet 46P, and then we have all the parameters. You can actually say now. So now what it does, it contacts the JPL horizon, which is the main repository for small body. Gets all the parameters about that particular comet, look for the right index for that comet, and it knows the distance, the location, and it will do some estimates about the activity based on brightness of the comet. JPL Horizon site is a little bit slow, so it does take some time, but for example, the machine found that this is a periodic comet. Every time it comes to our, next to us, it has a different orbit. So the machine picked the closest orbit, and it has to give you the record that it did for that. So in this case, it tells you that the comet is around 1.2 kilometers. It gives you some basic density, some parameters of how far it's from the star. Of course, it's a G-type, it's our star, our planet, our star, sorry. And then you tell, it tells all information about how far it is from us, 0.8 astronomical units. So it gives you an information basic about the comet, got from that. And if you go back to the atmosphere, so now I feel all this stuff here. And this is for this particular comet. The first thing it did, it created this activity number, which is how many molecules are coming out of the nucleus. If you're a cometary scientist, that number is very revealing. And the machine did some voodoo magic to get that number. It's explained in the paper and other stuff, but it does some idea about the brightness and uses the brightness of the object to estimate the activity. So the number normally comes out to be very reliable. And the temperature, and another equation used to estimate what is the temperature of the comet. And you can see there are all these molecules here. Because a comet is in fluorescence, all the things I told you before about exoplanets don't work for comets. They have an exosphere. So here you need to have this non-LT code, which is the thing that we developed here at Goddard. These are non-LT fluorescence codes for all these molecules. And you tell it, you know, this is water, is 100%. And you also have to give this number called the lifetime. What is the lifetime? Because it's an actual exosphere. The molecules are coming out of the nucleus, and then it's a certain time they die. And you need to quantify how many molecules are dying to know what is your true column density. So that number is about the lifetime of the molecule. And again, you come here. In this case, we're using Keck, the NIRSpec Keck. We put this range, the resolving power of the instrument. In this case, we say, I want you to put me at 4,000 meters from the surface of Earth. And I want you to have 1.5 millimeters of water looking up. So it means that we are looking at the comet from the surface. The telescope is located in Mauna Kea. And these are all things for NIRSpec. You synthesize it, and it gives you something like this. It says it's going to be very noisy because the comet is not very bright, but it gives you how the molecules will look like and the sensitivity you will do to get that. And you can do zooms, and again, you can look at the signature for that comet. It also tells you the transmittance of Earth, and you can have an estimate how well you can do. So if this is for the infrared, I have a template called optical wavelength. If you load that one, if you synthesize that one is in the optical. So in the optical, this is the optical in Armstrong. You can see all these bright features. These are fluorescence codes for comets. And you have many the C2 stretch here, the C2 lines, and then you have OH and stuff like that. So you can also model in the optical. Okay, and now the last thing I want to talk is the transmittances of Earth. So I just show you right now, I pick a particular condition for synthesizing things from a template. You know, I pick a Mauna Kea and I pick a particular amount of water. But what happens if you want to synthesize precise, accurate water, terrestrial spectrum, transmittance spectrum? So you need to have this telluric transmittance template. So what is it? I want to show you how this look like. So first of all, this is how the radiance look like at this wavelength, looking up from nighttime on Mauna Kea, for example. This is how the transmittance look like and all the subcomponent, the molecules doing that. If you want to download this, you click here. And it will give you a file that looks like this. You can save it and you can do your stuff with that one. And the thing about this is, let's look at how the configuration is. First of all, we have Earth, and we have these things remain the same, obviously. Earth is around always a G-type star. And we are saying here, we are looking up from Mauna Kea, and we are looking at 35 degrees into the horizon. So if you are in the surface of Mauna Kea looking at that angle, this is where you define the geometry. So if I say this, ephemeris. So once you put the right date, the machine now is going to pull out the information about Mera. So it will give you the right profile, and it will know everything about your atmosphere at that location. And the thing about the calculation here, you see, it has all the parameters for you to calculate the accurate calculation. It has the angles, it has the location of the planet, and you're on Earth. And then if you come to the atmosphere, you have a nice profile, you know, the water profile, all the stuff about Earth. So now you can go back and synthesize, and you can pick any wavelength. We can do it again, this one again. And then you have this, you see, apparently it's much more water, so the lines look broader than before, I had before, and you can look at different. So that's the basic of this. So you saw that this is the GUI, and I don't want to be longer, but I want to try to explain how to run this in an automated fashion. So the GUI is very powerful, and again, this is the typically way you typically run things. And actually, I recommend people to always play with the GUI first. You should be able to do everything you want in the GUI. But imagine that you want to do a complicated simulation that you want to synthesize 1,000 spectra, and you just want to tweak the time of day, or you want to play with the methane abundance, you want to run them in a cadence. So if you do it by hand, it will take you a lot of time. So what we have is something called the API, or the the program interface. So what it does is, if you come to just back to this, if you come to this file, so remember, this is the configuration file that we've been editing all the time. We do things. It looks like this. So one of the things you can do is you can send that file to a NASA server, and the NASA server will give you back this. Sorry. The NASA server will give you this file back. So you send the config file, and the server will give you this back. So correct. So I will show you. You just send a config file to the NASA server, and the NASA server replies to you with the radiances or the transmittance, whatever you ask for. Okay. So how does actually this works? So if you go to remote operation, the API system. So this is how it typically works. You have your own machine, and you send this config file, which is send you. And then machine will do all this stuff, and it will reply to you with another text file with Spectra. So it's supposed to be very straightforward. And so you can have your own little script, IDL script or Python or any code you want that edits that file, make changes to the file, and then you send it to the machine, and the machine will return you Spectra back. So the way that is done is this. You save that file as a config file, looks like this. And then you type this command like this. You say cur, which is the way to communicate to servers. You say use that config file, it's a text file, and give it to this address, which is PSG API. You give that, and the PSG will give you back a spectrum. So it's pretty straightforward. And that's what people are using with the API. There are more explanations here. You can play with this. I would definitely recommend to go for this. But it's very straightforward, and once you learn to use the API, it's very nice. People ask me, can you do more stuff with the API when the GUI interface? In reality, no. The GUI interface, the web interface, at the end of the day, is a text editor for the config file. Whatever you can modify in the web interface, you can modify with the text file. So at the end of the day, it's the same thing. The key thing for you is to understand that this is the way to control this. There's an issue because the tool has become very popular. I get too many API calls, and I'm getting 1 million simulations requests per month, which is a lot, just to the API calls. So what I've been doing is I've been restricting the servers to 1,000 simulations per day per user. It's a way to keep not burn the servers. So and some people I gave them keys, so you can add a key and you can do more. But in reality, is you can do the calculation for you. The other problem is that every time you do this, imagine you are in Europe and you want to do this. The file has to fly to Maryland here, run here, and then send it back. It's very inefficient. So there's a moment when you can run the API, but you start getting frustrated that it's too slow, and you want to do it in your own machine. You say, great, but I want to do it in my own machine. So this is where we come with the Docker thing. So what is Docker? So the problem is that, as you see, PSG is a pretty big package. There are a lot of databases. It's actually pretty huge. So how do you ask people to install it? It could be almost impossible. So what we've done is we created a package. It's like a virtual machine of PSG. And you can, what you do actually, you install a mini PSG in your machine. So you are installing like a subversion of PSG. It's like a subcomputer that looks like PSG in your own machine. Docker is the most popular out there virtualization system for software. And we implemented this with Google. Google was the one who introduced me to Docker because Google wanted to compute 10 million Spectra. And they asked me if they're going to use the NASA servers to do that. And they wanted to train some exoplanet thing. It was pretty cool, actually, working with them. And when I was talking to them and say, they gave me access to their servers, and we installed versions of PSG in their servers. And the way to do it was, what our approach was to do with Docker. So Docker is a pretty powerful way. Once you get it running, it's the good thing. So what do you do? You install Docker in your machine, and then you do these commands here. You do pull, you install the thing, and then what it does, it creates like a server, virtual server that is in your machine. So instead of having all these things sent into our NASA servers, now you only do the curl commands. But instead of having the NASA server, now it's your local host or your own machine. And if you do it that way, it's instantaneous because obviously it runs in your machine. So how does this thing look like? So let's see. I don't have it running. Sorry, guys. I'm gonna run it right now. I'm gonna do. I'll do my help here. So this is how you run it in your machine. Okay, now it runs. You have to install Docker first. It's I wouldn't say it's super easy, but it tends to be pretty rather easy. So when you run it, something like this will appear in your. You will see something that looks like this. This is your local version of PSG. Because PSG has almost 1 terabyte of data. If you want to run it in your machine, you need to install 1 terabyte. You need to install 1 terabyte packages. But most of the people don't need 1 terabyte. Most of the people just need very small packages. So what we did is we divide the blocks of PSG into modules, and depending on what you want to do, you can install different packages. So in this case, there's the program package, which is the main core thing. This is the base, which is a Hydran, some of the basic things. The surface packages, the atmospheres packages, the ephemeris package, the telluric, you can see all the things. Some of them are reasonable, some of them are huge. And if you want to do these calculations, you are going to need a lot of space in your machine, but it can be done. The thing is that every time you say they're not installed. So imagine that I say, also the machine keeps track of, for example, it tells me that there's a new version of the programs that released actually yesterday. And you say, and the one I have installed is from January 24th. So I say, I want to update that. You can click here and you put update, and it will update the thing here. And if I don't know, I want to install nothing, not that big. Let's do this one here. So if this is what it's doing, actually contacting the PSG server, and it's going to be downloading 2 gigabytes of data to the Wi-Fi. I don't know how long it's going to take, but you get the sense. So this thing is that that's the way it gets the data from the PSG servers, and then it installs it in your machine. It's supposed to be straightforward, and it should work really well. So yes.
For the scattering, if you want to finish up.
No, it's fine. Tell me.
For the scattering calculations, it doesn't do any sort of statistical Monte Carlo like simulation for scattering with the phase function, does it?
No. So that's a good question. So the question is, how are the calculations done? So there are different ways scattering calculations are done. Some of them are statistical ones, like as you said, the Monte Carlo ones, probabilistic ones. The one I'm using is what they call the die sort mode, which is what you do is you characterize the phase function by an analytical function, which is a Lagrangian polynomial. So you actually capture that probability by capturing the legendary polynomials. The more legendary polynomials you put, the sharper that phase distribution becomes. But the good thing about what I like about the legendary polynomials is that they are phase complete. So Monte Carlo codes are, you need to put a lot of phases, and if you miss a lot of them, you become very incomplete solutions. They are good for very accurate and very target things, but when you do a generalization like this, I think the die sort mode is the best way to go. Okay, now you see how it works. So it's downloading, and yeah, maybe I shouldn't have to. Yes.
How many people does it take to maintain this?
Well, so the funny, so this started like a hobby thing. So actually, it has never been officially funded to this thing, only for very small funding. But the thing is that I use it for my own stuff. So the good thing about what I like about the tool, and this is what I think is the main thing. So I use it for my ExoMars work, and by doing that, I improve all the time the codes. But then I know that other people can use the improvements that I do for exoplanets or other stuff. So at the moment we're trying to focus on the future, and we're trying to compartmentalize. But incredibly, it doesn't take a lot of work. Of course, it consumes a lot of my time, but it's great because I also improve my own code. And the fact that I get feedback and say, I think you're missing this thing is wrong. Can you fix it? And if I fix that, I fix my own retrievals. So you gain from all of that. And I didn't show, and I wanted to finalize here. The other big thing about this is the retrieval part, and I'm just going to finalize with this. So what we've been talking about now is all about forward calculation, but we never show how you just get information out of Spectra, which is a big thing. So this is now we're using actually 4-hour retrieval ExoMars and many other stuff we're using for this. So this uses the optimal estimation, which is the most common thing. And I'm going to show one simple case just for simplicity. I can show this one for example. Okay, so this is retrieval part. This is how, imagine that I went to Keck, I took my Spectra, and it looked like this. It has a wavelength, and it has some funky shape, roughly calibrated, but it's not perfect there. So then I need to retrieve, this is actually a retrieval of water, a heavy water on Mars, HDO. So the first thing I did is I went here and I say that it's Mars at that time. I put all the stuff about Mars here. And then I hit here some basic stuff. Okay, first of all, I say that the units here are web numbers. Then I told the resolving power of the instrument is 33,000. We will convert the data to that. The radiation unit is IRF. How big was my beam? 1 arcsecond. And then I say I was in Mauna Kea, 4,000 meters, all the stuff here. And I say the machine feed the telluric place too. Then I also say the gain. What is the gain? This thing is not flat, perfect flat. So I tell the machine to feed the second order polynomial to the shape of the continuum. I also say that there are, you can see some stuff like here. Those are fringes that they are typical for this instrument. So I say remove at least one fringe from the data. Also, there are solar features in the spectrum. So I tell the machine remove the solar features. And we can leave it there. And I also say what you want to retrieve. In this case, you can pick stuff. And you can say feed water on Mars. And you can say what you want to feed. And what I'm going to do is I'm going to feed the GCM value, and I'm going to scale it till I get a match. And then you can feed other stuff. You can feed the profile of CO2. You can do whatever you want. But let's go with this one, and let's do retrieve. So it did the fit. It's actually a pretty good fit. And it shows you here the results, the reduced chi-square, the number of parameters, the degrees of freedom, how many fringes you remove, how long it took, and give you the abundance of water on Mars and the error bar. Yeah. Yeah, sorry.
We have an online question from Luisa at Granada.
Yes.
She's wondering whether the aerial instrument template is functional.
No. So the Ariel, if for people don't know, it's an exoplanet mission, been recently selected for ESA, and I've been talking to them. I added the template. It's in my machine, but the Ariel because they don't feel confident about the specs of their instruments. They asked me please not to have it on the tool. So I've been talking back and forth with them, and I say, well, until they lock their specs. Once they are happy with their specs, I will put them back, and we're gonna put the numbers back. Yeah, but it's there. So yeah. Go ahead.
How do you model the fringe?
Yeah.
It's really amazing. How do you model them and what? And then subtraction. I mean, do you have a user input or you just guess from the spectrum?
No, the machine does a parallelogram analysis. So if that's a feed, and then you see the fringe at the bottom. So for example, if I go back to the thing. So if I don't remove the fringe, you will see it pretty evidently. So you can see it looks like that.
Right. So it relies on the spectra.
So it looks at the residuals,
Okay.
then computes a parallelogram analysis, fix the things, get the phase amplitude, and take them out. And then the key thing is that the retrieval, if you look at the report, and just to finalize, these are all the things you need for a retrieval. It tells you the chi-square, the average kernels, all the parameters for a classical retrieval you want, the degrees of freedom you got, and the Jacobians for this. You can also do them for comets, and this is I'm going to show the last retrieval. So if you do comet infrared retrieval, this is a comet Bottini. You see we have a spectrum that looks like this, measured with Keck also again, and then we say retrieve, and it does the fit, and it gives you all the bounces in the comet and the stuff like that. So you can read the documentation, but the idea is that you can compare spectra and stuff like that. So that's all. If any, okay.
There's a few more online questions.
Okay. Yeah. Just yeah.
Okay. So Louisa had another question.
Yes.
She's wondering whether there's a high resolution mode available for instruments at Hermanus at Cata Alto.
Cala Alto. Yeah. So I didn't the Carmeners. It can be added here. I didn't. So typically, what you do is you can just come here and define it yourself, the specs of the thing. Normally, what I would do is I just pick a near spec, but instead of being Calo Alto, you can say lower altitude and change the altitude of the telescope. That will be, and then you can put any resolution you want here. So at the end, the instrument Carmeners in Calo Alto is very similar to the near spec. It's just a shorter wavelength range, but it looks very similar to this. The specs of the detector are going to be very similar. So make sure you just put the right diameter of the telescope, the right altitude, and that's all, and you can do it. So it should be fine. You can create your own Carmeners in some way.
Thanks. And there's another question from Stefan in Innsbruck. He's curious about the aerosol scattering
Yes.
of ISIS. If, for instance, I use Jupiter and keep ISIS at a default mode,
Yes.
the deep feature known at 0.59 micron.
Yes. Let me look at Jupiter.
Yeah, maybe you can read the question.
I can just say it about it.
Okay.
So yeah. Just to talk about for some of these particular cases of scattering, you can see Jupiter is very peculiar. It has these layers of ices and stuff. So these scattering things you do, you pick here. In this case, I put the ammonia for Martin Chick and the water ice from Warren Ice. This database from ammonia is very, very rough. It's based on optical constants, which are from the 80s, actually. If you download it here, this thing is from 84. So this thing is very, very old. So, and it is a mis-scattering code based on that. So take it with a grain of salt. It's better than nothing. But I consulted people about it. This is the best we have right now, unfortunately. The more we can get better constants, the better we can get ammonia thing. For water ice, there's more stuff. The Warren database is actually pretty good. So it should be fine for most of the cases. But again, you can play around. You can modify these layers. These are just ideas about templates where things should be.
So there's one more question from Nick here, and he's wondering whether users can provide their own lines.
Yes. So you can see every database. One of the things you learn about databases is that every person uses a different format, unfortunately. And so normally I've been holding, if you look at water, you can see there's Geisa, Hydran, and some other ones. The user cannot provide a line list, but it can provide cross-sections information. So typically you come here and you put add a spectroscopic file. You tell what type is it. It could be any of these things. You give it a name, and then you say the units of the wavelength, and then you load it and you can provide that. So people can put their own stuff, but it's only intended for cross-sections. Because line lists are so peculiar for every system, I have not allowed people to update any line list yet. But if they provide it in some sort of standard format, I may add it later. But for the time being, only cross-sections as for molecules. Okay. Well, so again, we're running a bit late, but thank you for being here, guys, and for the people online. So, okay. Bye-bye.